Welcome back to the third segment of overview of site remediation. Today we're going to be speaking about technology options. A wide variety of options exists, and the goal of this segment is to provide you with a very brief overview of what are the options, and not specifically the design details associated with each of the underlying cleanup technologies. We have heard in the last two segments, if a subsurface contamination exists and will pose an adverse risk, then action is required. There are three possible ways to control those actions or to treat the problem. One is to protect the receptor, perhaps putting a drinking water treatment system at a well. One is to treat the source, that is to take the source away, and the other one is to cut off the pathway or treat the pathway. The general strategies for site remediation are very broad categories, are completely removing the source and or plume containment, or possibly reducing the mass in the source area or within the plume, thereby getting the concentrations down or below regulatory standards. The technology development triangle here from the book by Panka and Cherry, very clear that the technologies begin perhaps at a lab scale. So let's assume you have compound A and B in your hands, and you think that adding compound A and B into a contaminated area will actually destroy the targets of concern in that area. You would begin by developing those on a bench scale or developing what is called a laboratory proof of concept. Then if that were successful, you would then advance yourself to small-scale field trials, into pilot-scale trials, into full-scale trials, and then ultimately, if you were successful and perhaps rich, you would then be able to promote a full-scale field trials or exposure across multiple sites. So the technologies work from those in the experimental stage to emerging technologies, finally up to the end of those that are proven technologies. Now, not all proven technologies that sit on the top of the technology triangle here actually work across all sites and all problems. They have their specific areas where they work and a specific either geological conditions or perhaps contaminant types where they won't work. So let's begin by staring at the concept of source removal. That is simply having to dig and dump, remove the contaminated soil, perhaps dewater the area with a dewatering system using cut-off walls to lower the water table, transport the contaminated soil to a landfill site, or perhaps treat on site as a ex situ treatment process, perhaps with biopiles or a soil washing system. Very high cost for very small volumes. And of course, there's a restriction on the depth and the ability to deal with contaminated soil under existing surface buildings. Here's an example of biopiles where you create windrows of contaminated materials, add in oxygen and nutrients to encourage biodegradation. Here's a example of a pulled underground storage tank. Here's what is left under the underground storage tank, clearly impacting the soil under it, and perhaps if enough mass were released, having the mass migrate all the way down to the water table. In other situations, it's very common to create a much bigger dig and dump area. Here's an area close by to where I live where they dug the complete foundation of the building out, installed in a very elaborate dewatering system in place, into tanks, Here's an idea of the scale of the dig. And in the end, they built some very nice, high-priced apartments. When we then stare at other ways to deal with source containment, one would be those that are physical barriers, such as a wall or a box around the source area. So the standard approach here is either a slurry walls with bentonite and soil, or perhaps cement and soil, a grout curtain, either liquid slurry or emulsion material, or perhaps an interlocking sheet piling wall. All of these are clearly restricted by depth and the ability to work under existing buildings. Here's an example of a sheet pile wall, and here's an example of a slurry wall. Both of these are very well understood. They're both engineered containment systems. Well, if we don't do physical containment systems, then the other choice is hydraulic controls. Here we have an example of a source area with a dissolved phase plume that emits off of the source area and ends up in a nearby receiving water body. We could place an extraction well down gradient of the dissolved phase plume, extracting the fluid from the ground, thereby restricting the plume entering the receiving water body. Other options for plume containment deal with a series or a row of passive release wells, perhaps a reaction wall, or perhaps a funneling gate. Here's an example of a funneling gate. The idea of the funnel is to funnel the dissolved phase plume into the gate, and within the gate it could be filled with some reactive material that will degrade the contaminants in the plume. There are both key gates and hanging gates. A fairly standard and historical approach, probably the most well-known groundwater cleanup approach, is called pump and treat, where we have a plume and a source zone. We install a down gradient extraction well within the dissolve phase, pump the extraction well, thereby restricting the migration of the plume. It's very well understood from engineering and science perspective that we can predict the capture zone very well of groundwater extraction wells. There are many tools to help us optimize and design a groundwater extraction well. So from a purely engineering perspective, it was very convenient for us to begin by putting in a well and extracting from the well. Well, when we put in the extraction well and we move the well closer to the source zone, we actually increase the flow rate through the source zone. We increase or enhance the mass transfer, and this leads to a degree of source zone treatment, and it's no longer just plume containment. So let's consider an example here. We have a 1 meter cube block of aquifer material, porosity of 30%. Let's assume we have 2% of the porosity filled with naphthalene. Assume we have a velocity of 10 centimeters a day, and we would like to know how long it would take for us to remove all of that naphthalene mass. So again, here are the data. How long will it take to remove all the mass? Well, you would think it's a hard question to answer, but in fact it's not. Here's the answer. We calculate to start off with the mass of naphthalene. That is approximately 6.8 kilograms. If we assume that all of that is at the solubility level in the pore space, that is approximately 0.009 kilograms of dissolved mass. Take the amount of mass of naphthalene, divide by the mass in the dissolved phase within 1 pore volume, and you would very quickly see you would have to pass through 760 pore volumes of fluid in through the 1 meter cube block. And that would take, at that flow rate, approximately 10 days for 1 pore volume, or for all of the mass, 21 years. So you can see it's quite a long time to actually use an extraction well to remove the mass within a very small source zone. So the goal then of the pump and treat was very quickly understood that it was a plume containment, and for it to treat a source zone or to remove mass within a source zone, it would be very hard. Here's an example of a pilot scale experiment where the concentrations within the extraction well that were comprised of cis DCE, TCE, PCE started off at very elevated and stationary or equilibrium levels and then quickly tailed off. The axis on the y-axis here is a log scale axis. This long tailing is due to the fact that the mass was removed fairly quickly from the high permeability zones. The presence of the non-aqueous phase liquid caused sufficient mass to replenish that mass. We ended up with non-ideal mass removal. The mass was removed quickly, as I say, from the high permeability zones, but the other remaining mass was diffusion controlled, which then led to, as I said before, the inability of a pump and treat system to treat a source zone. Now, the pump and treat has been around for quite some time, and the life cycle analysis of this system is well understood. So the components of a life cycle analysis would involve an estimation of the design life, the treatment process, likely water is the extracted fluid, there may be an airstream as well. The effluent from the well would contain organics and inorganics that would have to be treated. There would be a price on the equipment, chemicals, energy, and flow rate. Oh, and the concentration profile start off very high, as we saw in the previous example, and then tail off. So the entire system becomes over-designed to account for the magnitude changes in concentration over time. The plume itself has its own life cycle. The stages are the expanding phase, where the plume starts off, will grow, and the mass flux coming out of the source zone is much greater than the assimilative capacity of the aquifer. Then the plume becomes a stable plume. There's no change in the plume. A shrinking plume is one where the source has been depleted and the plume will shrink. And of course, an exhausted plume is one where there's very little concentration left and the entire source mass is gone. The figure on the left here shows a result from a plume study, and you can see that approximately 37 of the plumes studied, of over 604 plumes, are approximately between 100 and 200 feet in length. So the question is, why do these plumes get formed, and why there's such a abundance of short plumes? Of course, these are petroleum hydrocarbon plumes. Well, that's because the plumes that are formed from petroleum hydrocarbon source zones, or any other type of source zone, are impacted by the natural attenuation process within the aquifer. It is a viable remediation approach and involves the dispersion process, absorption process, a degradation of the dissolved phase due to biodegradation or hydrolysis reactions, perhaps to a degree a bit of dilution from surface water recharge and mixing, volatilization from the interface between the soil air and the water table, and diffusion process. These are all processes that move towards a loss of mass within the plume. There are protocols and guidelines that exist to demonstrate that natural attenuation is actually working at a site. Now let's go back and think about those techniques which will actually remove mass from the source zone instead of the plume. Well, it comes to say that if you can remove the non-aqueous phase, then that should be your first approach. Clearly, that would involve pumping. Here are two sketches A and B, where we have a dual phase extraction system. We have a conventional well where we pump the aqueous phase from lower depth and pump the floating L-maple product from the top. Clearly, this is the best way to remove mass from the aquifer. Another way to remove mass from the source area is through bioremediation or bioaugmentation. That involves adding nutrients and electron acceptors to the source zone. I think you'll hear more about this by some other speakers. A very convenient way to remove mass is through a process that involves in situ flushing. That is the injection of a chemical reagent in one well, the extraction in the other well, and the fluid or the in situ flushing fluid would then bypass or flow through the source area. In situ flushing has been defined as the injection of a solution into a source zone with downgrading extraction and above ground treatment and or re-injection. Well, what is the choice then of the flushing fluids? Well, they can be ranged from water, air or ozone in an in situ air sparging application, surfactants, co-solvents, reductants, or oxidants. The goal here is to create an in situ reaction zone where you reduce and destruct mass, thereby you reduce the strength and lifespan of the source zone. Let's just have a peek at a few of these. In situ air flushing with air. Here we have a case where our source zone is above the water table and we put in an extraction well and we pull on the extraction well, and that will cause atmospheric ambient air to pass through the source zone, and that is called soil vacuum extraction, or SVE. Works, as I said, in the unsaturated zone, involves a phase transfer to the air phase, can be operated as a pulsed case, and in some areas that might be called bioventing, because you're actually encouraging atmospheric air that's enriched with oxygen to come into the source zone, and you shut down the extraction system and allow the oxygen to act as a electron acceptor. You could have in situ flushing with water only, and that is called water flooding. You move more water past the source zone than you would in ambient situations. That would increase the mass transfer from the non-aqueous phase to the aqueous phase. However, if the flow rate is too high, you can displace low viscosity naples. And sometimes you may increase the temperature of the flushing fluid to enhance the mass transfer rate. If the flushing fluid happens to be surfactants or surface active agents like a soap, you would then enhance the solubility, perhaps lower the interfacial tension of the compound which may lead to levelization, you need to match the surfactant to the contaminant. And sometimes, since surfactants are very expensive, you may want to recycle the surfactants. In the case of co-solvents, which are normally a mixture of water and alcohols, for example, ethanol and ethanol, they would then enhance the solubility of the non-aqueous phase liquid. If the flushing fluids involve a reductant or oxidant, these compounds promote a reductant or oxidation reaction. Possible oxidants are peroxide, permanganate, and persulfate, and possible reductant is iothanite. Well, another way to remove mass is through thermal methods involving steam flooding, thermal conduction heating, or electrical resistant heating, ERH. All three of these deliver the energy in different ways. However, the same end result is the goal, and that is to increase the temperature of the subsurface. An example of steam flooding is here, where you create the steam on the surface and it's injected into the target zone to vaporize or ovalize the contamination. So that's a very quick overview of all of the technology options. We began this segment of the course on why we want to remediate. We've then talked briefly about remediation of actives, and finally I concluded here with a very brief overview of those technologies that one may employ to clean up a contaminated site. And that's all. That concludes this lecture on overview of site remediation.